Hello, my name is Brittany English, and today I will be presenting my project. So as a background, cerebral palsy and stroke are two examples of debilitating neurological disorders that can permanently damage a person's motor function or muscle coordination. For this project specifically, we're looking at the rehabilitation of a damaged wrist function, as wrist function and hand function are the most important factors for perceived quality of life. And the reason for that is because if one has the ability to use one's hands, they're able to do personal activities such as feeding, going to the bathroom, and dressing. And without that, you have no independence because you're relying on a caretaker to provide those personal activities for you. So we saw the greatest ability for patient improvement here with the wrist rehabilitation. So I'm going to show you a little bit about the process of what happens when you suffer from the reduction of motor function. So first you'll have that injury, you'll see your doctor and be identified as a candidate for rehabilitation. Then you will go to a physical therapist. You'll meet with them approximately once a week for an hour and learn some therapeutic exercises. Then you'll have to go home and do these exercises by yourself for about an hour a day, and then return the next week. And you'll repeat this process for months. And at the end, if you've participated in that at-home portion, you will have improved motor function and an improved quality of life. So that's great, but the biggest problem with that is that this therapy, it's not fun, it's boring, it's painful, and people don't want to do it. So if you're bored, you're going to have a longer recovery time. So there's really a great value in engaging the patients in the process, making them more likely to participate, which will shorten their recovery time and improve their quality of life. So currently, robotic exoskeletons are used as a way to help out with this engagement and that at-home portion of the therapy, but they're designed in a one-size-fits-all for an average adult male. So women and children are much smaller, and so they may not be able to use these technologies, which is a huge problem. So we have come up with a solution to make our own exoskeleton, which we made a 3D CAD model for, and we're able to 3D print any size. It's easily scalable. As you can see here, we've designed one for a petite woman. It has a potentiometer on board and that reads the wrist position, and then some electronics transmit that via Bluetooth to a tablet and uses that wrist position as a video game input. System was designed with the following specifications. The hardware shown here is easily scalable, it's lightweight, it's able to fit patients of all shapes and sizes, and it's low cost. And our software, we did a variety of games to allow different choices. We designed them to be enjoyable, habit-forming, and to have the ability to adjust difficulty. So here's one of the video games that we designed called Robo Blaster. In this video game, you are a spaceship shown here, and you're continuously firing lasers. And those lasers, you're shooting at asteroids which approach you, and then you can destroy them and succeed. And our second game here we call Robo Rock and Roll. This game is designed to be similar to Guitar Hero. You're a guitar pick that moves up and down, and you're trying to catch these music notes that are approaching you while a coordinating song is playing. So we did a series of experiments to validate the effectiveness of our system, and here's a summary of those experiments. First, we did an engagement experiment where we asked participants to wear the exoskeleton, and they were asked to do 2 tasks in a random order. One of the tasks was to play the tablet game until they became bored, and the second task was to exercise until they became bored. And then afterwards, we asked them a series of questions about the experience. Then we did a movement experiment where we asked the participants to wear the exoskeleton to play a series of levels that were designed to encourage very specific therapeutic motions, and we recorded their wrist positions and their paths during this experiment. And finally, we did a small validation experiment where we asked a participant to come in and complete a series of exercises wearing the prototype exoskeleton that we designed and a commercially available exoskeleton. And we counted the number of exercises and the amount of time that the participant needed to spend resting. So as a summary of the results from these experiments, from the first experiment where we tested engagement, the participant spent 4 times longer exercising with the video game than they did without before they became bored. And then from the survey questions, the participants reported that they preferred the gaming experience to an exercise-only experience. From the movement experiment, we were able to show that when we provided motivation to follow a specific path, the participants followed that path pretty closely. And then from the exoskeleton validation, we showed that participants were able to have a more productive exercise session with the prototype because they were able to complete more exercises and spend less time resting. We contribute that to the prototype being more lightweight and more comfortable. And I would like to thank everyone who helped me out with this project. Thank you so much.